So it's my honor and a privilege to introduce Dr. Pan, a very distinguished professor. He has spent over 20 years in the area of deep learning and bioinformatics. He is in fact one of the best in the country and the world in the area of bioinformatics. He has published a large number of papers, grants, and he's a Regents professor and chair in the Department of Computer Science at Georgia State University. So let's welcome.
Professor Iyengar, thank you very much for your invitation and introduction. Now, today's talk is really about deep learning, right? So if you know some deep learning, we can exchange after the meeting. If you don't know anything about deep learning, I hope after the meeting, roughly you understand what's the meaning of deep learning, right? So that's the purpose of my talk. And of course, in computer science, everybody knows deeper architecture usually is better architecture. So your addition, you use log steps better than horizontal. And this is the example, log n and so on. So many people know deep learning, deep neural net is a good idea. 20, 30 years ago already it is. But why deep learning suddenly become hot area, right? The reason is the name, suddenly become name. And also a few technology changes. So what's in deep learning and neural net? Neural net, basically, you have a few layers, you have neurons, and we change the neuron, right, connected by weights and values. Then somehow, in the future, whenever I have input and output, if the output always say yes, and the reality is yes, good, don't change the weight. If the output is no, but the reality is no, yes, contradiction, you need to change the weights. And eventually, after million training, the weights is so good, then eventually, whenever you give me a new input, 99% success. That's the idea, right? Now, so here, there's issues. It's called vanishing gradients. Whenever you have a deep neural net, deep means what? I have so far away, I change my next layer is easy because the gradients change. I say, oh, go up, go down. How much go up, go down? It's easier. But after 100 layers, the value disappears. It's like a stone put in the water, right? Initially, the ripple is big. After 100 meters, no ripple anymore. Vanishing gradient. Overfitting is another problem. So deep learning already 30 years ago have theoretical concepts. Never working. Why? Because it's a problem. Now, how to issue this problem? Of course, the last point is this. We need to training algorithms sophisticated, meaning complicated algorithms, we can overcome the problem. But if you can overcome the problem 30 years ago, also people have this idea already. But why 30 years ago is still not successful? Give you an example. If I design sophisticated algorithm, should work. But this deep learning take me what? 30 years. 30 years training is impossible, right? So not working. So right now, deep learning is successful because deep learning algorithms plus data, big data suddenly available. And GPU, parallel computing power, cloud computing, suddenly available. Before 3 years computing time, now 3 minutes we can perform. Now, oh, it's working now. So what's deep learning? Deep learning basically is a concept of deep neural net. 30 years ago, already have this concept. However, we need to add some new algorithm to change the vanishing gradient issue so that it's working. So that's called deep learning, right? So that's why in the paper, some people call deep neural net, some people deep learning, subtle difference, right? New algorithm. So in the hierarchy, basically AI is a big picture, and inside the AI you have machine learning, and inside machine learning, deep learning is a particular case of machine learning. Basically, for example, AI. 30 years ago, my teacher, like Bruce Buchanan, produced the first expert system. Diagnose your disease, right? Basic feature. He knows, okay, you have fever, temperature, your yellow color in your mouth, okay, your eyes have red eye. These features put in computer, and they say, yes, this disease or that, right? These are called human hand design the program. Hand pick up. Deep learning the model basically what? You don't need to give me anything. Google's test basically what? You give me 1 million pictures, right? The million pictures, half are what? Dog. Half are cats. They just go in, and then I give you a cat, if the reality is cat, right? No changing weights. If I give you a cat, you say dog, okay, change your weight. Now change your weight, how to change your weight? First, I have to calculate this weight. You have so many weights, right? You can name the next one. The weights have to, each weight, you have to decide, go up or go down, right? Second, go up how much? How much means what? It's the basic rate change. Now, you can imagine go up or go down basically what? Depend on gradients, basically derivative. I want to go up or go down. Go up, I will change the value so that closer to your result. I won't go up, I'll go down. Now, change it go up, how much is the issue? If you change it too much, meaning the constant too big, what's the problem? Vibrate. Change it up and then next down, change up, it's not working. Now, change a little bit is better, right? Gradually changing better. But if you change a little bit better, too small, what's the problem? Your training time will be 1,000 years. Because you change it not enough, always a million years change it. Okay, so you have to change all these, right? So I can give you one example. This is my students' program. A few years ago, suddenly the deep learning is hot. Why? Because the machine beat the Go player, the champion of the Go player, right? And we did this, and we're successful. And the company purchased by Google and $1 million because this is a game, right? So my student, based on the paper, basically the paper is published in Nature, and our students implemented the same program with our feature, and we beat their program. Here, beating means what? In terms of accuracy, we played together with this field goal, we winning 85%, and the AlphaGo, this AlphaGo is from the company, only 11%. We beat them, right? So now, after this program, I said, maybe we should write a nature program too, nature paper, right? To beat them, and my students said, yeah, we are working on this. Now, don't misunderstanding my issue, right? You cannot say, okay, after 1 year, how can you beat this paper, right? Because we stand on their shoes. They are the greater person still, right? Basically, we are still using similar, but you can see the features, we added a few features. So without their foundation, we cannot even do it, right? So don't confuse it, we are great, we are good, but we are still standing on them, right? Reality. So now my student said, we can do it, I have to spend another half year, we can beat them further, right? Then after about a couple of months, right? Suddenly you remember AlphaGo 0, AlphaGo 0 is the next version. And then my students say, okay, I'm not going to do it. Why? Because their idea of next step, future idea, very similar. Exactly the same, actually. The only difference is what? Using my hardware in my lab, using the data they provide, the algorithm we are inventing similar to that, AlphaGo 0 plus code, right? AlphaGo 0 code. We need 1,100 years. Now, 1,100 years, even though we are smart, we have everything, we cannot perform because even after 1 year, it's already obsolete, right? So we give up. But this story basically tell you what? Right now, AI, not only intelligent, you need to available data. Where's the data? Because these data, these Go players map, right? 5,000 years, all these great players accumulate together into this. But this story basically tell you what? They tell you, actually, even AlphaGo or deep learning, they are not intelligent, they are not smart. They just play the game, statistically play better than you. Example here. Here, this one map, right? You only have 3 colors, white, black, the other called blank. So wherever you have this map, what's my next move? Basically, statistically learning and the mapping based on 5,000 years map, right? I determine the next stop. Most probably, I'm going to win. So that's why the player play with the machine, right? Sometimes players get lost. How you stupid? Why you put this player next step here? Because random, statistical, there's no connection. There's no intelligence here. Say I'm going to kill this group. No, there's statistical. So that's why deep learning actually, in my term, right? So far, all these AI actually not intelligent. They are so far deep learning included, right? They are called data-driven. based on so much massive data, decide the best choice for the future. So now let's talk about we have so many architectures. I'm going to discuss this. So optimization, what's meaning better deep learning? Basically, you optimize these weights so that in the future, when the same domain data come in, 95 or 98% we can recognize correctly, decision making correctly. That's the idea, right? So today I'm going to discuss all these challenges. Now, these challenges are my own challenges. Basically, I presented to myself, and then we have solution or partial solution. So any challenges, much more, right? Of course. But these are our challenges. We have partial solution. And one by one, I'm going to discuss it briefly. And of course, if anyone interested in my work, after meeting, I can present further the papers and also detailed discussion, right? Yeah. So first question is architecture. Now, what's meaning new architecture? Deep learning means what? Now, this is traditional, it's called CNN, convolution neural net. Why CNN is working? Because CNN is very suitable for images, 2D architecture, right? So one layer by layer, just recognize feature, then eventually yes or no, recognize. The Google's that dog, cats, is typical. And dog image, cat image coming, and training the weights, and finally 95%, if it's dog, it's dog. If it's cat, it's cat, right? Training the weights. Now, imagine in our brain, our neural net is not like a linear connecting. Should be complicated, right? Our linear array is more like this, more like complicated. Now, if we construct this neural net like so complicated, so far it's not working because we don't have the technology or capability yet. So we design basically the control rule we design is called cross-layer architecture. This is just a name, right? But forget about cross-layer, basically it's like this. We call the short circuits. Remember, last time I said vanishing gradient. Vanishing gradient means what? The water cannot travel too much. If you are 100 layers away, if I change the weights, eventually you receive 0 signal. Why? I cannot change the weight. If I cannot change the weight, meaning what? I cannot train it anymore. The accuracy cannot improve because you are not to change it. You are refused to change. Now I said jump. Yeah, you are 100 layers away. How about I from here jump to 10? 10 immediately jump to 30. 30 jump to you. Only 3 steps. Now I can change your weight. That's the idea, right? So we jumping. Now these are just concepts. Now you can say, ask me, why disconnect this like a loop and a hierarchical and the block. Lot of experiments and a lot of paper reading and finally come up solution. But the basic idea is what? I'm jumping to reach this idea. Now, so using this one, we can see ResNet, the best one from Google, and we can improve further accuracy. The error reduced, right? 7% becomes 6. And we can also see here use ResNet, 110 layers, which this one, actually in our case, 26 layers enough. Because we jump, right? Now, many people may think you can see for 50, of course, beat them more. And if you use 110 below, we can beat it further, of course. But this will take a lot of time. And further, because we beat them already, the paper is enough, right? So you can imagine this. So this is another data. We can say 26 layers, we actually beat them already. And this one, ResNet, is 1001 layers. And we beat them already. We only use 26, right? And this paper published in Top Journal already. So just to give you the flavor and what we are doing, right? Yeah. So we have ResNet. This is before cross-layer, the new architecture, and right now highways, other people's architecture, and this is our architecture, and this is not published yet. It's ongoing. What's meaning highway? Highway basically, I'm reaching for you 100 layers, too far away, but there's a switch there, on and off. On means what? Because I bypass this neuron. Off means what? I bypass you. Bypass you means what? Bypassing. So even I from here to reach 100 layer, actually I may bypassing many. I reach only 3 steps. That's the idea. This is another paper. This is our paper, short circuits. Short circuits again, you can basically say we change the formula so that coming back, jumping around. Now, in picture we say jumping around. In formula really means what? Means change of this formula, additional formula. Let me show you the formula. This is a paper going to be published. Short circuits like this. Okay, short circuits gradient. so you jumping around, right? So this is also like a jumping from this layer, I'm jumping here, this layer from jumping here. And this is different from the cross layer, the formula is different, and we are, this paper is under review, and the result is much better. You can see here, compared with the traditional one, we are training speed is much better, right? So in deep learning, basically, what's meaning better? Actually, so far, we only improve two things. If you have network, 100 layer, I have 100 layer. If your training time is 100 hours, I'm training time only 1 hour, I'm better. The second thing is what? Accuracy. If the accuracy is same, training time is better, it's better. Another thing is you train 1,000 hours. I'm training also 1,000 hours, but the accuracy I improved is also better, right? Accuracy versus time, all these two better, of course better, right? So this is just a flavor here. So the next question is deep learning with high dimensional array. High dimensional array is very tough. For example, this case is a 4D, right? This is 3D. It is 3D. Now, 3D image, you can use this picture. It's called a spatial dimension. 2D is a 2D image plus 3D, basically is what? A spatial dimension, and you come in, and this kernel now, before it's 2D, now use 3, we can solve the problem, and still same architecture, solve problem. Perfect. Now, why we say 3-dimensional, 4-dimensional in deep learning not working? Why? Because whenever you have a 2D, right, suddenly it becomes 3D. This is like a loop. The time increases exponentially. So in other words, 2D training time maybe 1 day, 3D suddenly become 3 years. 3 years for basic practically is not useful, right? So how to solve the problem? We have some ideas. Now this is still 3D, and this is further 4D now. 4D means what? Means this is called the functional MR image. Functional means what? Means different time I'm measuring a brain. The brain is still slides, right? So 3D. And then different function. For example, you're reading, you're sleeping, you are eating, you are watching TV, and this time is along the time. And this is 4D. So aside to the 3D, go to the import, and so timing is also another sequence. This is case is 1 to 200, right? So now, how to solve the problem? Our solution is use a 3D deep learning neural net, and here use LSTM, long short-term memory, because this memory machine can memorize history. The first go to here, and then go to second step, go to 100 step, and all these memory there, and this remembers the fourth dimension, basically time. And in this case, we can improve the result and got the better, got the results. And another possibility, use tensor to reduce dimension. Basically, implicate the tensor, implement the tensor in a layer. Neurons already have tensor, and we can solve this problem. And also, I'm proposing using PCA component, principal component analysis, reduce the division, dimension, and SVD, singular value decomposition, reduce dimension. Now, dimension, right? What's the purpose? The whole purpose is you want to reduce the dimension. On the other hand, the error message is still no, it's still accurate. So both working, then it's good, right? The next step is hyperparameter tuning. So whenever you have a deep learning, anybody today, you can download the code and put the import and working. Of course, the accuracy may be what? 70%, 65%, 63%, not working. So many people will ask me, why is it not working? Because not working, the hyperparameter tuning is not there. Because whenever you have the data, right, you come in with a deep learning. How do you know this deep learning need 50 layers? How do you need this function? How do you know this issue layer, how many neurons? All these are hyperparameter, right? And this hyperparameter has so many possibilities. How do you know which is best? Now, in real life, ideal case, if you have unlimited time, you can change every possibility. So 50, 100, and so on, all the parameters, and then try training the best, right? It's possible. But we have we only have limited time, so we cannot do this. So we are using genetic algorithm to attack a few points and optimize. And we experimented, and so far, for example, all these are population, and these are parameters, different parameters like operation include this, and the activation function, and the ReLU, and all the pooling use max or use others, and the channel. Anyway, these are just different parameters. And after that, you can see as the time generation going up, this result is going better, right? So now, of course, experimentally, of course, this is true. Whenever you're training more time, you get better results. And you can tuning eventually say, oh, 50 layers is the best. And the neurons, each layer, you should use 25 neurons and so on, right? Get the best results. And this is the same thing. And you can see here, in our case, if you just use random search. Random search means what? Means you don't know anything, just hit, right? Now, of course, to be fair comparison, you have to have a time, right? All of them running about 30 hours. You can see using genetic RNA search, we are much better than random search, of course, better than traditional genetic algorithm, and much better than evolution, and we are the best results.
So there is one other search called taboo search.
Yeah, taboo search basically is like a brute force search, probably like this one. So it's not good because your search is not intelligent. Our search is what? Well, we hit this guy, and then the next mutation a little bit better. Keep. Taboo search is like, I don't care about history. Right? Hit this guy bad, hit this guy still bad. I don't care, just a random search. Of course, take a long time. So fair search, actually we are taking less time. Now, why we say 30 hours? Because basically, after 30 hours, cut off. What's your best result? Here, we run in 24 hours already better than that, right? So this is another issue. Encoding scheme also important. Question. Oh, question?
Yes, very quick question. I'm sorry. The fourth dimension time. Is there like what's the increment of the polling? Because that's going to determine how much space and what kind of machine you need and so forth. Is it a millisecond? Is it every 5 milliseconds? Or
no, based on the loop, basically is exponential. So, for example, if the fourth dimension, let's say is 200, right? This will be 400 more. It's not like a fourth dimension only multiplied by 2. It's 400 more. Why? Because dimension is the loop. Imagine this 4 loops there. First loop is 100, second loop 100. The fourth dimension basically another loop. And plus the training is so far away. So it's more than 400 times. So before it's 1 hour, now it's 1 month, basically, right? So that's why we need to reduce from 4-dimensional data, hopefully to 3-dimensional, even to 2-dimensional. If the accuracy is almost same, it's for the results already. Because otherwise, 4-dimensional data, if the data is big enough, right, you cannot do it. Imagine the image, MRI image.
I think his question is like how frequency-wise, since the 4th dimension, the time series, you are asking like what is the slice you took it, like every minute, every half an hour, the FMI.
You are talking about this picture, right?
Yeah, fMRI picture, that's what he's talking about.
Okay,
Yes.
This picture, in our case, I can show you, in our case is what? About epilepsy disease, probably is a few hundred times. You know, because basically the step is usually is maybe even a few minutes away. Answer your question.
So that's
Yeah, that's what. And basically, you want to after a few minutes away, we want to measure the function different. You're reading, you're doing this, and it's different image, and we see the changes. That's the idea, right?
right. Thank you.
Thank you. And now, encoding scheme is also important. Many people say deep learning is not working in my case. Why? Because even though you have a raw data, you need to encode correctly for the deep learning so that it's working. So give you an example, genomic data, biology, right? Genomic DNA data, what's meaning DNA data? You can see DNA, you can high volume, you can generate a model training and a test model and the protein coding region, and all these are, we have algorithms we already performed, right? The question is what? Import still, what's mean DNA sequence? DNA sequence is the ACTA only 4 characters. What's mean protein sequence? Protein sequence only have 20 characters. But if you use these characters, these are designed by biology. They just use random name, right? But these are not working, right? When I say not working, name-wise it's working, but for deep learning, may not work. Give you example. Here, I have so many encoding schemes, right? Binary coding, chemical, biochemical coding, and so on. All these coding meaning what? I embed biological knowledge, property into the code. Give you example. let's say sequence 20 protein sequence basically means what? Inside each letter is called amino acid. Amino acid A, B, C, D, and so on, 20 letters, right? Now, if you are A and A, of course you can use the name A and A, right? But if A and B mean what? A and B the distance, meaning A can I mutate A to B easily or difficult. So imagine this property, right? If A and B can mutate easily, means what? They are mutatable, their distance should be short, actually. Even A and F, in whole life, almost impossible to mutate. A and F is so distant, I cannot mutate to you. Then our distance should be long, right? Meaning cannot mutate. So you have to embed this kind of information in the sequence, in the embed. So how to do this? And of course, there's so many things. Now, arbitrary means what? DNA sequence, CT, I just use number A102. And this one case use EIP, use a real number. See, complementary use negative, right? And enthalpy use this kind of thing, entropy use this kind of, statistics use this. Basically, I want to, like I said, analyze the biological properties so that each number, each value give a particular name, particular value. And this value usually have a better result. Okay, so this is just an example. And we just write a survey paper, surveyed more than 45 encoding schemes, and let the people know the pros and the cons. And each one have no absolute value say this is best. Because how about you consider biological property? How about the physical property? How about the chemical property, right? All these properties you want to embed it inside is not easy job, right? So our next job is what? That's a beautiful result. Can we use mathematics? In deep learning so far, right? Deep learning so far, many people, you design deep learning, Google, I design deep learning, I say your result based on this data set, 90% accuracy. And using my scheme, I improve to 94. I'm better, publish a paper, right? There's no theory, just structure change. So this paper is interesting. We first use mathematics to prove our solution better. Now, this is autoencoding. Many people heard the name. CNN is convolution. Autoencoding means what? Meaning every time, every layer you take care of yourself, and then ripple effect disappear, no vanishing gradients. That's the idea. That's called new algorithm. And what's the idea? Idea is basically saying the pre-training and the fine-tuning, basically I use this one. Layer, import, go to next layer, then find an output and get the result. This is architecture, and each layer, each neuron, I should draw this picture this way, but somehow. The import is X, right? Go to the neuron, and then this is output. So autoencoding saying what? Autoencoding saying, your input is X. Can you generate a function, some function, so that the output is almost equal to it? Now, many people say this is identity function easy, right? If you generate 1, 2, 3, 9, this 1, 2, 3, 9 easy. Why is it difficult? Because I want to have this function once finished, fixed, right? Any number should be same. That's difficult. Identity function is easy. Now, the second thing is what? Difficulty is what? You can see the picture, right? I give you 6 numbers, 1, 2, 3, 4, 5, 6, right? I require you to compress into 4 digits. 6 to 4 digits and 4 digits are compressed back to 6. They are same. Now it's difficult. You want to give me a picture, function. Anytime 6 becomes 4, 4 becomes still same. Now, wherever the same, actually never be same, right? We only say the length, distance between X and X star, output input distance what? Minimize. Hopefully 0.1, if you're better, 0.01 better, right? So that's a minimized function. And people claim using autoencoding, as long as I'm taking care of you myself, my input, my function, output is almost same. Next layer, input, output almost same. After 100 layers, this signal never disappear. You can still change. Drop down. And this is an outstanding paper. That's why whenever you see deep learning, you can see deep learning with autoencoding successful, right? That's the paper. Now, next one, a lot of theory, but I want to skip this theoretically. Next one saying, it's called denoising autoencoding. What's mean denoising? Your data have a lot of noise. So by import, using this input, I randomly remember, denoise, delete some data, and compress, and then uncompress. I hope this input is out. Then distance the smallest, drop that down. Now use this algorithm, of course, another paper. Basically, this paper claims what? This denoising algorithm really better than the original. Claim, good, right? This is good.
Can I ask a quick?
Yeah.
Is denoising is equivalent to eliminating features?
You can call this one, but they use denoising. Basically, not delete the import, not the feature.
Oh, okay.
Yeah, delete the import. So I randomly delete the import. This is neuron, delete the import, not the feature. Yeah. So little bit different, right? Now, next person design another algorithm saying, okay, now you have this denoising input, right? I'm using a different game. I'm saying what? This input X, I'm encoding into H, hidden layer value, and this hidden layer value 4, I delete randomly. And then go to this encoding, and then encoding to this one, and then minimize this, and then they claim this input, this output, right? They claim the algorithm working. And wherever you say claim the algorithm working mean what? Based on the standard data sets, you perform better, right? So in deep learning reality, if I have designed algorithms, if I test only one data, they criticize. Say, oh, that particular data not working. You have to use standard data at least 4 or 5. Tested by everybody. Standard sets is working, then it's better. So claim better. So our trick is very simple. Combine what? Both algorithms. Now algorithm, this is called the hidden layer denoising, right? Because auto-encoding, denoising, hidden layer denoising, 3 algorithms so far, right? Now we combine them together, it's very simple, it's called what? Double denoising. Very simple, right? We combine what? This is very simple. Import, denoising, delete randomly, hidden, delete randomly, go there, and then this formula basically consider this X and X star smallest, plus this H and H smallest. Now the number is important. What's the weight? If the weight is too big, you consider only this, delete this. If the number is 0.001, this disappear only this, right? Now, you sound like, okay, this algorithm is very simple, combine 2 papers together, right? The only contribution now is what? We mathematically prove. You can read the paper. Mathematically prove this algorithm better than all of them. Equal or better, and mathematically. Now, wherever we say mathematically, really mean what? Statistic. Statistically, based on certain distribution, we can perform either better or at least equal. And this paper is strong. That's why I have so many theorems. And of course, this is require at least 2 hours explanation, but people can read. But basically, this idea is, you can see, in reality, out of so many, these are big data sets, right? Used by popular people, popular deep learning, and we always beat them. This is our results, right? You can see 19, and we always beat them. And summary basically is what? 90% beat them. And out of the 8 data sets, we can beat them 6 or 8, 7, basically. Now, many people may ask me this question, right? Theoretically, you prove mine is better than all of you. Why still you do experiments? This is very similar to what? In networking, theoretical analysis curve is what? Smooth curve. But you still need a simulation to what? Random the analysis one. The simulation validated the claim. The reason is very simple. If you assume this data is based on certain uniform distribution, whatever, are they real? So we basically assume this is true theoretical results, better than all of you. We also use certain data, and this data is basically what? All of them using these bigger data, cheaper testing algorithms. We show experimentally we are still perform better thing, right? And so this is our results. And the next one is logical reason. This is a very interesting topic. So far, in deep learning, just data driven. No logic, no reasoning, no intelligence. So imagine, now I always think about it, and this is really, if you collaborate, we can continue, right? I have no solution, but we have preliminary results. Imagine Google's result, right? You are deep learning dog. Yes. Okay, no change. Dog, but this is a cat detection. No, I don't change the weight, right? It's very, very stupid, right? Dog, cat, dog. After million, then training, now you start training. The weight is fixed. Now, a picture coming dog, 95% I said dog. 5% said. But there's no knowledge. So I ask my students, say, beside the image, can you put the human being's knowledge into the image? Example, let's say a dog picture and a cat picture, right? Dog's ear may be a little bit bigger, comparatively, portion. The cat's ear may be small, but the dog's nose usually bigger, cat's nose is small. All these shapes, can you use this knowledge embedded there, perform better, right? So these are the ideas, and that's why we can apply knowledge. Before execution, we already have knowledge. And deep learning is a black box. We cannot do this, and can we add a logic reason, right? Now, adding this logic, what's the goal? The goal, the objective is basically improving the accuracy, prediction, right? Prediction accuracy. And inject prior knowledge into learning, and we can high-level knowledge, low-level sensory knowledge, and all these reduce the training time and improve accuracy. Of course, eventually, whenever you say algorithm is better, always two. Accuracy improve and the time reduce, right? These are personal. Now, we have done preliminary results. Okay, we call it data augmentation. So you have a data and the Google stuff we didn't do, right? The cat is smaller, the ear is smaller, but the idea is very simple. We want to convert this knowledge into data, and this data into the formula in the tree. That's the idea. So I'll give you an example. We can convert the knowledge into machine learning and express by first order clauses, and the clauses then into a logic, true or false logic, and the logic then into what? Into a data labeling, and the data labeling then finally into a training data. So example here, what's the meaning? This guy can, it's a bird. This guy can fly, can lay eggs, mammal, and carnivore, and so on. These are properties. So I give a student an example, right? How do you detect it's a bird or it's a chicken? Our knowledge basically says what? Bird in the sky. Space. Bird. If it's on the ground, most probably it's a chicken because it cannot fly, right? But the bird could be on the ground also, right? So you have to detect both, basically the shape and the image and also the knowledge. Hopefully, basically, without knowledge, you achieve 87%. With this knowledge, achieve 93. That's our objective, right? So here, we convert this knowledge into classification into logic, and then logic into formula, into value, and the value into, eventually, into what? Into labeled formula. Eventually, what's in deep learning? Whole thing deep learning is what? About the gradients. What's mean gradients? Gradients basically derivative. Derivative means what? This particular weight. In this cycle, you should go up, go down. Go up how much, go down how much. And by using this logic into the formula, we change the formula, hopefully improve. That's the idea, right? So, and understanding and this explanation also same thing, right? So wherever you say it's a dog, it's a cat, I'm asking you, why you think it's a dog? Deep learning cannot answer this question. I don't know. You just say dog. Why? Because it's statistical learning. It's statistics, basically, right? There's no reason, there's no logic. So we want to see how much, and one possibility to use visualization, and there's a paper published by Computer Magazine already, basically use color. Which feature dominating this one? So you say it's a dog, right? The feature will tell you, oh, dog, because this guy, the dog, has a big head, bigger ear, and the eyes, relatively big, and so on. All these features contributing 95%. This is dog. Tell me the reason, right? Deep learning right now, no reason. Just like dog, black box. So we are doing research in this direction, and the future knockout is another possibility. Future knockout means what? Means I detect this dog and the cat, but I knock out certain features, see the difference, and of course, if we knock out this feature, the difference is so big, means what? The feature plays an important role, this feature dominating 50%, the second feature dominating 40%, and so on, right? So these are our research results. And of course, from shallow to deep in the future method, wherever you do understanding, initially very shallow network, we can understand what's going on. Then deep really means what? Improved accuracy. So shallow to understand the feature, deeper to improve the accuracy. And eventually we know both features and accuracy better, right? So this is a trade-off, but no perfect solution so far yet. These are all. And finally, I want to say multi-view. Multi-view is we are doing this with what? Basically multiple source, right? Multiple source. Yeah.
Yeah. So in the previous section, so when you are training with those features like the extra features, including human being input. So, for example, when new data comes, like the new image from the dog, how you do know the value of the extra features?
I see. So after training, training is finished, right?
Yeah,
now the new picture coming is a dog. I think this one can use image processing software, right? So when I say knowledge, right? Let's say knowledge mean what? Means if this ear is bigger, relatively speaking, right? This head ear is bigger, it's a dog, right? Ear, the nose is small, is a cat. And then use image process detection, and this area is easy to search, right? And so this whole square is 100. This is only 3% small, 5% is big. This knowledge important, right? And of course, this is besides deep learning. This is what is called pre-processing. You need the image processing software to capture the feature, extract the knowledge from this image, and then import it. Does it make sense? Yeah. And it's possible to do it, right? So, multiple view. Remember, we have a 3D feature, right? In our case, we detect a disease. So we have MI image, functional MI image, and the other is what? Doctor's knowledge. So in the past, without vision, without image, basically doctor look at your X-ray, right? Oh, it has a black point. White area, how much? Oh, maybe you have lung cancer, right? All these are doctor knowledge, right? So this is one. And we put this doctor knowledge converting to value. And again, like you said, machine instruction. Automatically use machine, right? Because this is a picture, MI image, right? I can extract this area, how big and so on. Now, what kind of information there? Basically, volume left this, volume gray matter, and so on. And these are doctors, how many? 51 features. These are features doctor use in when I see an MI image, I say, oh, you have this disease, you have cancer, what? Based on this knowledge. Now, doctor knowledge is not complete, not perfect, right? So, second view, but we speak importantly, we use this feature. Second view is what? Is MI image, 3D, and the import of the deep learning. Third one, functional MI image is for 3D, but you can use LSTM, and then we combine together, we further use a deep neural net, and the voting. And basically, neural net is different from, you have three, right? You can vote into there like equal voting, right? The two is a one, this is zero, of course, two. But we are using neural net basic training this link also, and eventually 1 or 0, right? And this result, you can see the result, finally it's called 3 view. Our 3 view, if we use the doctor knowledge, very low, actually. Why? Because doctor knowledge, how do you know 51 is enough? Maybe more features, right? Yeah. Use this one better and this one better, but combine together the best.
So in the previous slide, how do you combine different features at the end?
This is the voting. Basically, you give me a yes or no, right? Epilepsy disease, actually, in this case. And you say yes, this is yes, yes. 3 yes, of course, yes, right? It's a no, yes, yes. And we train this one, and this is weight. We train with a real result. So eventually, this weight, this may be only 0.3, this is 0.5 the weight, right? And this may be 0.6, mean what? This is majority weighting, this is heavy, and after training, these weights fixed. Yeah. So all these weights, even data dependent, are not pre-decided. I'm not saying this link is your voting power is 0.33, 0.33 equal, right? I'm not doing it. Maybe this is less than 0, depend on data. And we get a result, it's better than results. So basically, we can reach you 93 best, right? And then this will be lower, but most are lower anyway. Now, this paper published, right? So many, we published so many news. The news, and even Yahoo News contacted me. Why? Because astonishing. Because doctor actually less than 70. So in the future, you can imagine our deep learning algorithm can beat all the doctors. That's no question. The only question is basically is the legal issue. right? Legal issue. Because even use doctor knowledge, 30% is incorrect. Does not matter. The patient will not sue doctor because they assume doctor is not perfect. But if you use a machine, even 99% accurate, one is wrong. And in China recently, one cancer patient, right? And the machine detected Huada gene company, big company. They detected no cancer. Then they have second screen. The doctor say, "Oh, Huada, their machine said no cancer." I look at it because it's very big anyway, right? The doctor said, "Oh, no cancer." Then the second doctor also check. Check is very careful. The second doctor say, "Okay, machine said no." The first doctor said no. I look at them. I find it they. I maybe said no. Okay, after a few days, died. It's cancer. Now patient sue the machine company and sue doctor. So, but in reality, many people do misdiagnose your patient, right? But in machine, this is a problem. So here, this is the problem. And the last one, we are want to use the intelligent freezing layer. Intelligent freezing layer basically means what? Meaning, wherever you have so many layers, certain layers never change too much. Can we freeze them if you are not changing too much? Now, there are some certain ideas, and basically, I give the students ideas, basically. If they change below delta, let's say, you don't need to perform computation and bypass them and continue and save time. And the result, you can see the result basically. Of course, when we use this one, it's complicated formula. Basically, it's what some of them and below certain threshold, we can say yes to do freeze or no, don't do freeze, right? And randomly do freeze and so on. And finally, you can do layer to layer freeze and which layer to freeze and so on. It's complicated, but the idea is what? We want to design an algorithm intelligently freeze the layers so that reduced time accuracy is not reduced. That's the idea. And here, experimental results, and you can see here, the original one, accuracy is this, and taking so much time, are reduced to freeze. Now, these are the network, traditional network, right? So we can see here, time, compare this one, reduced 10%, 7%, and accuracy is almost same. Yeah, almost same, basically. So this shows by intelligently freeze certain layers, we can reduce the training time, but keep the accuracy. So this is our, and this one, same thing. This is just different data, right? 80% reduced, but the accuracy is actually increased a little bit, right? Actually, but I can say this is a statistical error. This actually increased a little bit, basically same, right? No change. Yeah.
Yes, sir. I have a very specific case. I came back to the university to graduate from the university, and recently, it was very wonderful to see that you're doing this kind of research, and given that my actual only daughter was diagnosed with epilepsy very recently, so I'm very interested in this kind of research. I think that the most useful thing would probably be analyzing the prognosis, like how effective would be, because diagnosing epilepsy or skin cancer or whatever it is, it's usually kind of very, doctors have especially if you go to one or two different doctors, they usually have a good sense of whether the person has this kind of disease or this other kind of disease. But I guess the real challenge is to determine, and I think this is the most
Determine the reason.
Yeah, so should we discuss this after the talk, because there are some people that will go.
Oh, okay.
So the students also want to.
Yeah.
Oh, okay.
Yeah, and the last topic briefly, right? Amplification gradients. This is topic interesting. Remember the ripple effect, right? 100 layers away, the water going down, ripple, and the ripple, no effect. So my idea is that students, can you artificially increase the value? Yes, going down, 0.1, 0.11, and so on. But how about this increase? Then we call it boosting. And the value of the gradient is vanishing, gradients vanishing, and we boosting them basically what? Change the data amplification. Dynamic value this, and all these are complicated, but there's a lot of skills. Boosting which one? Boosting how much? How frequent? And so on. And we done a lot of experiments, and this is the code we don't have to discuss. And experiment without setup, and finally we can see the results, right? I think we want to see the results. And basically, the final result is by doing boosting, the percentage of error percentage is by about 2%. Sometimes right now we have new code about the 3% is possible in certain data. So at least this is direction. You said gradient vanishing is a problem. Can we artificially increase your value? Yeah, decrease, disappear, smaller and smaller. I multiply value. Intelligently multiply formula. Somehow boosting use get better. And when we use boosting gradients, right, research paper, there's a paper on boosting grades already. However, this is totally different idea, but they use the name already. That's why we use our name called what? It's called augmentation, the amplification. So it's different, but basically boosting the gradients and perform better and so on. So today's talk, basically, we discuss so many, and each one we present a challenge, we present our preliminary results. Some are already published, some are even in writing stage, some are finished but submitted. Right? So solving some of the deep learning problems. Thank you very much.
Thank you. I think, there are some other people that have to go for a different topic. So Dr. Pan is going to be here to meet with students and some questions. So please continue your conversation.
Yeah.
I'll be back.
Okay.
I'll be in my office.
Okay.
Yeah. Thank you.
Thank you.
Wonderful talk.
Thank you. Thank you. Yeah. Your question.
How would you determine the number of layers for a neural network, for a deep neural network learning, and how do you pick the number of neurons in each layer?
Yeah, it's a tough question. Remember, there's a guy from Stanford, he's teaching deep learning, right? He got hired by FIU, $2 million annual salary, and he's a hot person. His idea is what? Whenever you give me any data, after a few tuning, he will have a sense how many layers, how many neurons you can get. It's called super parameter tuning, right? In our case, how do you know this 100 better? We can use binary search, of course, easiest, right? So initially 100, is it working? And double 200, and then if it's 200 is worse, 150. Double search, binary search, right? And then jumping around, you can decide which is the optimal value for number of layers. Is the first thing. In terms of number of neurons each layers, you have to test binary search also, but roughly you have to have a rough idea because this domain, this work is similar to that, should be similar idea, right? And in our case, use what? Genetic algorithm. And my slogan is this, right? Genetic algorithm is basically my slogan. As long as you have unlimited time, unlimited CPU power, I can always optimize this neural deep learning to the best. And running, eventually best, right? And this is very similar to compiler. Why do we need compiler instead of machine code? Machine code is more efficient. Compiler is what? More tedious and complicated. Running time more, right? But a certain time, training time is longer, even take you 1 year. Once training finished, the code will reduce time is worth it. Compiler, same thing. Why people spend 10,000 man years for the compiler, tuning a little bit, right? You spend so many 10,000 man years to open a compiler. The reason is eventually the object code can save you, each time save you 1 second. It's still worth it. Why? Because once the compiler finished, everybody running the code, saving time. So the training time, same thing, right? Even though my genetic algorithm, let's say, optimize the layers, take you 1 year, optimize. Once optimized, give you a solution, you can use the industry, each time save you half time, it's worth it. So you can only say there's no theory to tell you this data. How do you know it's 100 layer or 1,000 layer? You don't know, right? You have to decide. And usually, if longer layer, more layer, accuracy can be improved. However, degrading is also happen, and if too long, they'll be not working. So you have to find the optimal solution for this particular data, but based on experience only.
So yeah, I'm more curious about the intelligent freezing of layers.
You're working
so
same? Okay.
No, it's happening in the training or validation or testing
In the training.
phase.
Training. Once training finished, testing is exactly the same. Yeah. In the training, basically training, how often you have to freeze? How jump? Usually I don't freeze in each layer, right? I'm jumping every 10
Isn't it kind of tuning the layer?
Tuning the layers, yeah, yeah. And you need the formula and a lot of experiments, yeah.
Is there any mathematical formula about which kind of hyperparameter will work?
No
or
formula.
which kind of
No formula. Yeah. No formula. That's a pity, right? In the deep learning so far, no theoretical results. However, my student working on this, right? Genetic algorithm we already formed. The genetic algorithm formula is what? Tell you the time versus optimization quality. So he can tell you this formula, of course, based on certain assumption, right? So if you're running 1 hour, I can optimize to reach this point. Running 1 day, reach roughly this point, and theoretical. Now, we are trying to put this into optimization, right? There's a lot of issues. The issue is what? A lot of assumption in the formula. It's not perfect, but roughly you can do it.
On top of it, you have the data bias.
Yeah, data bias. Yeah, all this distribution you don't know, right? And now, actually, I think the first step, even though you have data bias, remember 30 years ago, queuing theory. Queuing theory, you assume the custom coming exponential time, right? Jumping. How do you do the exponential time? Maybe constant, maybe not. You don't know. But theoretically, Kleinrock, right? Kleinrock from UCL, he knows if exponential time, he can use the queuing theory to solve the problem. Without this distribution, I don't know, you don't know. So that's the only way. And then eventually you can relax and improve and so on to prove this model, exponential rival model, almost equal to reality, right? So this case is the same thing. We can assume something, first theoretically prove. Eventually you can improve, and this is the direction to go. Yeah.
Question about the sequences of the DNA.
Mm-hmm.
So you said you have to change it to
Some value, that's a real value. That's it.
that doesn't reduce the same
Reduce time.
or like any criteria for changing that.
No criteria. I mean, when we do this DNA, remember 4 values, 4 letters, right? If you use ADT, D, all these is just random 0, 1, 2, 3, 4 may not be good. But if you can put the chemical properties, biological properties inside is better. And again, biological properties so many. What to put is the issue. Nobody knows, right? That's why we presented 40-some the encoding scheme. Basically, this from this team, this from this team, all have advantage, disadvantage, and we need to at least learn and aware of the situation. Depends on application, right? Saying encoding really affect your results, right? So that's all.
Okay, let's give a big hand to Dr. Moore.